areas of concern are closed to seismic surveys. During operations, visual and acoustic monitoring is used to detect marine mammals that may be present. Seismic surveying uses compressed air released into the water to create sound waves that penetrate deep into the subsurface rock at the bottom of the ocean. To give animals that may be sensitive to this sound time to leave the area, the surveying process begins with a soft start, a technique that gradually increases sound to full operational levels. The survey is conducted by a ship towing a compressed air gun, which fires in regular intervals, and a large array of sound sensors that record how long it takes for the sound to bounce back from the layers of rock under the sea floor. From the recorded data, detailed three-dimensional maps are produced. These provide engineers the information they need to develop a production plan in order to tap the highest yield reserves. The maps also pinpoint the safest and most efficient drilling locations, eliminating
After the conductor pipe penetrates the seafloor, the drill pipe is released and pulled back to the vessel. A large drill bit connected to the bottom of the drill pipe is run down to the seafloor. The drill bit is led down to the bottom of the hole through the conductor pipe. The drill bit rotates and drills the sediment and rock below the seabed. Seawater is sprayed from nozzles on the drill bit to raise the cuttings to the seafloor. After drilling several hundred meters, the drill bit is pulled back to the vessel. A casing pipe, about 50 centimeters in diameter, is set into the drilled hole to keep it from collapsing. The casing pipe is run down through the conductor pipe and is inserted into the hole using the drill pipe. Cement is pumped into the space between the hole and the casing pipe to fix the pipe in place. After cementing, the drill pipe is released and pulled back to the vessel. The Chiku is equipped with the riser system in order to drill into the earth even deeper. As the riser pipes are added one after another, the blowout preventer is run down to the seafloor. The blowout preventer is connected to a wellhead which is located on top of the casing pipe. The vessel is now connected to the seafloor via the riser pipe. A drill bit, smaller than the one first used, is run down through the riser pipe and casing pipe. The drilling begins. Once the riser pipe has been connected, drilling mud is used instead of seawater. When the target depth is reached, the drill bit is pulled back to the vessel. To drill the hole even deeper, a narrower casing pipe is set in to protect the drilled hole. After the casing pipe has been installed, cement is pumped into the space between the hole and the casing pipe to fix the pipe in place. Again, an even smaller drill bit is run down through the riser pipe and casing pipe, and the drilling continues. Repeating this process, the Chiku will drill through the ocean crust to collect fresh, live mantle. This is something that has never been done before.
Seismic imaging, sometimes called reflection seismology, is an exploration method that estimates the seismic characteristics of the Earth's subsurface. The technology measures reflected acoustic energy waves and is mostly used for coal, oil and gas, and geothermal exploration. Seismic imaging provides geophysicists and geologists a method of mapping the subsurface structure of rock formations. Geophysicists and geologists interpret the data to map structural features that could potentially contain minerals, hydrocarbons, or hot rock resources. The Earth's upper crust is composed of many layers of rocks and minerals that all have different properties, such as hardness, density, and porosity. The placement and orientation of these layers give clues as to the likelihood of finding mineral, hydrocarbon, or hot rock reserves nested within them. Changes in properties between different rocks can cause reflection and/or refraction of sound waves. Seismic imaging works by sending acoustic energy waves created from a sound source through these layers and then recording how long a reflected sound wave took to be received by a microphone. This data tells geophysicists and geologists where rock properties change, thus helping find oil and gas deposits. Typically, there are two methods for producing the source sound waves. One is by using a vibrosize, and the other is by using an explosive detonation. A vibrosize is also known as a thumper or a shaker unit. It is a large hydraulic ram that is fitted to a special truck. The operator stops the truck at a location where they would like to generate a signal and uses the vibrosize to ram the ground, thus creating a series of source waves. Microphones, called geophones, that have been specially placed in an array around the survey area, pick up the reflected sound waves and record that data to a digital medium for later computer analysis. Sometimes, instead of using a vibrosize, explorers will use an explosive like dynamite to create the source wave. Explosives are placed beneath the earth in shallow drill holes. When the explosives are detonated, an acoustic shock wave travels through the ground and is detected by an array of geophones that have been previously arranged. Because scientists know how long it takes for sound waves to travel through and bounce back from different types of rocks and minerals, careful interpretation of seismic data can give geophysicists and geologists detailed cross-sections and three-dimensional graphics of the subsurface of a surveyed area. This can help them find mineral, hydrocarbon, and hot rock resource deposits.